Hello and welcome. In this video, we're going to look at this band stop filter. It's still an RLC filter, but this time our capacitor and our inductor are in parallel with each other, and that's going to allow a different response. The band pass filter allowed just the very specific frequency that we wanted, and that was going to be that FO, or that center frequency. And now this one's going to allow one frequency to be completely eliminated and all other frequencies to be allowed through. Our center frequency on this one is going to be a little bit more complicated to calculate because we have to include more of our winding resistance. So for that one, we'll say that our FO is equal to the square root of 1 minus our winding resistance, RW squared, times our capacitor and our inductor, divided by our inductor. And then that whole thing is divided by our 2 pi square root of L times C. And that's going to allow us to account for the winding resistance, the impact of that on the top, and then the bottom is just like we saw it before. 2 pi, that's our circle rotation, and then our inductor and capacitor under that square root equation. So we can plug that into our Desmos over here and say that we have, open parenthesis first, our square root equation on top, and that is 1 minus our winding resistance. We see that that's 8 ohms in this circuit here, squared. And that's multiplied by, and I like to parenthesize this just to be safe here, our capacitor divided by our inductor. So 150 pico, so 150 times 10 to the negative, up to the negative pico, which is negative 12. And then we can multiply that by our inductor. And that is our 5 micros. So we'll put that as 5 times 10 to the negative 6. And we'll close off that parenthesis and then the one on the outside, and then we can divide that entire thing by our 2 pi square root LC. Let's put that down there. We'll say 2 pi times the square root of the inductor times the capacitor. That was that 5 times 10 to the negative 6. And then that would be multiplied by our capacitor, 150 times 10 to the negative 12. And that is our total frequency equation here. And we've got 5.8 megahertz, 5.81 megahertz. And we'll write that down. We'll say that our FO, put it up here, FO is equal to 5.81 megahertz. We know that's megahertz because of how forward we can move our decimal point. Our decimal point's way back here right now. We can go forward 1, 2, 3 spots there, and another 3 spots, and put our decimal point right in front of that 5, and between the 5 and the 8 there, and that gave us that mega times 10 to the positive 6 location. Okay, so from there, we can use this to calculate our XL. We know our XL equation has not changed. That's that 2 pi FL. We now know our F, and so we can use that as our answer value for that one. And so we'll say that we have 2 pi times our frequency, that's the answer that we just got, multiplied by our inductor value of 5 micro. So 5 times 10 to the negative 6. And that is going to give us 182, and we can round that up, 183 ohms. So we'll say that the XL is equal to 183 ohms. And that's the resistance of our inductor, right? We call that the inductive reactance. So next we can use that to determine our Q factor, and that's going to be the quality factor between our linear and nonlinear components, specifically our winding resistance, because it's in the same branch as our inductor over here. So we'll say that our Q is equal to our XL divided by our winding resistance, RW. We'll set that out. We can solve for that in our Desmos. We'll send this one here and say that we have our previous value here, our answer of 183 divided by our winding resistance of 8 is going to give us 22.8. Round that up, technically 22.9. And that's a factor. So that is going to be our quality for that one. And we can use that to determine our total Z value, our Z value from purely resistive standpoint. And that's going to be ZR. That's going to be our linear Z value. And that includes the winding resistance as well as our Q factor there. So we'll set this equal to our winding resistance of 8 ohms multiplied by the Q squared plus 1. That's the equation for that. So we can plug in our Q for this one. That's 22.9. And we'll put that into our Desmos over here. Send this one out, and we'll say that we have 8 ohms for our winding resistance. And we can multiply that by the Q plus 1. So let's put that in a parenthesis just so that we get that plus 1 out of the way. Q squared is 22.9 squared plus 1. We'll add 1 to that and close that parenthesis there. And that is what we expect from that. So it's a 4.2 kilo ohms. So we'll say our Z is equal to 4.2 K ohms. From here, we can use that to determine our output voltage at its very minimum value. We can say that our Vout is equal to, at minimum, we'll put min in here also so that we can compare the two, because we're also going to get a maximum value. This one's going to be using our ZR. We're going to say that the RL that we have, which is 560, goes on top. We'll divide that by the sum of those two. This is going to be our total resistance, right? Because it's technically our voltage divider equation. So we'll say that we have 560 plus our ZR value of 4.2K. And then that whole thing gets multiplied by our voltage source of 10 VRMS. So when we plug that one into our Desmos over here, we can say that we have 560 divided by 560 plus 4200. And then we'll multiply that by our 10 volt RMS. And we're left with a 1.1, we can round that up, 1.18. So our Vout minimum, the minimum voltage output that we're going to get from this, is equal to 1.18 volts. And that's also a VRMS value. So when we send this one out, we can do the opposite. We can do the maximum output voltage, and that uses the full winding resistance, not the one that's a part of the quality, the ZR that we just found. So we're going to do the same equation, 560 on top, divided by 560 plus our winding resistance of 8. Right? And that's going to give us the maximum output. And we'll multiply that by our 10 volt VRMS. So our Vout maximum is equal to 9.86 volts. And that's also a VRMS value. So now that we have those two, we can measure our Bode plot and we can see where exactly this frequency happens at. So let's eliminate some of these calculations here, and then we will go after measuring our bandwidth, and then we'll have to convert that using a logarithm to get to our voltage output. So we'll pull out our Bode plotter. Our Bode plotter is on the sidebar here, the 6th one down, or we can go to our simulate instruments and we can go to the Bode plotter. And this one compares the front end of the circuit, the voltage, to the back end, the voltage out. And so we can place our input around the input voltage by grabbing our positive in line and going to the front half of our circuit here, right in front of our voltage line. The negative one goes to our negative side or ground, which is anywhere on this bottom wire all the way across. The second half, our output, is going to go around our output resistor, and that is going to be where we pull off of this circuit to go to another circuit if we wanted to filter the incoming and pull out the output. So we're going to put the output at the top of our resistor right here. That's anywhere on this line. And the negative side of this output goes to the ground line or the bottom side of the resistor. So the same spot that the other one was. So from here, we can use our Bode plotter to measure our voltage gain. And then we can use that to calculate the actual voltage at the minimum and maximum values here. Let's hit play. We see that we can hardly see the signal there, so we might have to scale our resolution of this circuit here. We can do 20 kilohertz on this one, and that's going to scale us a lot closer in on that resolution. And the other side over here, we can lower this decibel range down until we see a nice clean signal, and that changes that lower dip here. And we do see something different from the last one. The last one had an upward peak, right? Saying that I allowed that one location and nothing else. This one does the opposite. It allows all the frequency across the top and disallows, it stops this frequency down here, but allows everything else. So this is a band stop filter. The other one was a band pass filter. So from here we can use our probe line and right click and go to next minimum, and that's going to be that very lower end right there. And that gives us this decibel value. And also our frequency, right? It says that it's 5.754. Technically that rounds up to 5.8, and that's really close to our cutoff frequency that we expected. And so that is where we want to be. We're going to grab this decibel range, and then we're going to use a logarithm to rearrange that to solve for our voltage out. So our voltage gain is calculated using our voltage gain equation. It's a logarithmic equation. The logarithmic equations just basically say that it never actually reaches maximum. It gets really, really, really close and continues to get really, really, really close, but it never actually reaches the full. And so when we use logarithms, that's what we're talking about. We're talking about something that never quite gets all the way to the top. So in this one, we now found out our voltage gain. This is going to be the gain of it. And we use V gain is equal to 20 log of our voltage out ratio divided by voltage in. And that's what this Bode plotter is doing. It's got an input and output, and it's comparing its input to output, and it's giving you a decibel value for it on a logarithmic scale. And so we are going to use this equation, rearrange it, because we just got the gain. We just got 17.761. Technically it's negative there. And that is equal to our 20 log of an unknown V out divided by our V in, and we know that that's 10 VRMS. And so now we can rearrange this. This is actually a challenging part here because logarithms we don't usually rearrange too much. But we can divide out what we know we have. Let's swap a color here. We know we have this 20 at the front here, so we can just divide 20 to both sides. And that's going to be rearranged there. And it's going to knock out the 20 from this side and divide this one on this side. And then from there we can use our power 10 rule to rearrange our equation. Power 10 rule says that we can put 10 down and put it to the power of this output. And so that's going to be our negative 17.761 divided by 20. We can evaluate that. It'll give us a decimal range there as well. But that's an exponent value. We're going to put into the exponent of the 10. And then that's going to equal our V out divided by 10. Right? That got rid of the logarithm right here by doing that. And so we can plug that in and evaluate what that power factor is. And then in the end, we're going to do one more, right? We're going to multiply by 10 to both sides to get rid of the 10 on this side. So multiply by 10 here and multiply this entire thing by 10 over here. And that's going to give us our remainder. This is going to cancel out and we'll just have V out. So we'll have V out is equal to, and we can plug that into our Desmos over here. Send this one out. And we can say that we have 10, open parenthesis, times 10 to the, we'll go up caret here, and we'll open a parenthesis and put this division inside here. It's negative 17.761 divided by 20. We'll close that parenthesis and the next one there. And that is going to be what we expect our output voltage to be, right? That's our equal to our output. And so we'll say that that is 1.29 volts. Okay, let us know if you have any questions.